Hello and Assalamualaikum. Introducing my group member, Afiq Hafizin bin Mak Rahim, Muhammad Arif Khalish bin Saiful Izan, Afif Nazariff bin Abu Bakar, and my name is Muhammad Danial bin Muhammad Firdaus Balan. Today, I will present the introduction of our case study. Our topic is the collapse of an under-construction bridge over the Betwa River in Hamirpur district, Uttar Pradesh, India. The bridge was being built to improve transportation between nearby villages and consisted of reinforced concrete slab, bridge piers, and temporary supporting structure known as shuttering systems. Unfortunately, on 29 May 2026, part of the bridge collapsed during severe weather condition while construction was still in progress. The bridge was important because it was expected to improve regional connectivity, reduce travel time, support economic development, and provide better access for local communities. Now, I will continue with the bridge specification. Next, I will explain the bridge specification. The bridge was mainly constructed using 4 key structural components. First, the concrete deck slab, which forms the surface of the bridge and carries traffic loads. Second, reinforced steel bars, which are embedded inside the concrete to increase its tensile strength and durability. Third, concrete piers, which act as the main vertical support that transfer the bridge weight safely to the ground. Lastly, the bridge rely on temporary support and shuttering during construction. This temporary structure held the concrete in place until it had fully hardened and gained enough strength. All of these components play an important role in maintaining the stability and safety of the bridge throughout the construction process. Now I will pass the presentation to the next presenter. We will explain how the bridge collapsed.
Assalamualaikum warahmatullahi wabarakatuh. So I will explain how the bridge collapsed. So the bridge collapsed during the construction stage after a severe storm with heavy rainfall occurred overnight. Strong winds created excessive lateral pressure on the partially completed bridge, while the temporary support and formwork were unable to withstand the additional loads. As a result, the concrete slab, supporting structure, bridge pier, and shuttering system failed, causing a progressive collapse. The collapse trapped several workers beneath the debris, resulting in 6 fatalities and multiple injuries. Investigation suggested that extreme wind loading, inadequate temporary support, construction stage instability, poor load distribution, and possible design or construction defects all contributed to the failure.
Next, I will explain the mechanics of material analysis for the bridge. First is the cross-section or beam shape. The bridge deck behave like a beam because it carries the load from vehicles and transfer it to the support. The beam cross-section is very important because it determines the strength, stiffness, and resistance to bending. A properly designed beam can safely support heavy loads while minimizing deflection. However, there are some possible issues. If the beam depth is insufficient, the bending resistance will decrease, making the structure more vulnerable to failure. In addition, during the temporary construction stage, the bridge may have experienced reduced structural stability before all components were fully connected. Next is the bending moment. The bending moment represents the internal force that causes the beam to bend under an applied load. The formula used is M equals W times L divided by 4, where W is the load and L is the span length. For this example, we assume a load of 100 kilonewtons and a span of 20 meters. By substituting these values into the formula, the bending moment is calculated at 500 kilonewton meters. A higher bending moment produces greater internal stress within the beam. so the structure must be designed to safely withstand this force. Now, I will explain the maximum bending stress and yield stress. The maximum bending stress is calculated using the formula sigma equals m times y divided by I, where m is the bending moment, y is the distance from the neutral axis to the outer surface, and I is the second moment of area. Using the assumed values of a bending moment of 500 times 10,000 power 6 Newton millimeters, y equals to 300 millimeters, and I equal to 4 times 10 power 9 millimeters to the power of 4, the calculated maximum bending stress is 37.5 megapascal. Next is the yield stress. For typical reinforcing steel, the yield stress is approximately 415 megapascal. Yield stress is the point at which material begins to deform permanently. In this analysis, the calculated maximum bending stress of 37.5 megapascal is much lower than the yield stress of 450 megapascal. This means this bridge remains within the elastic region, where it can safely support the applied load without permanent deformation. However, if the maximum stress exceeds the yield stress, plastic deformation begins, which may eventually lead to structural failure. Therefore, based on this analysis, the bridge is considered safe under the assumed loading condition.
Moving on to the technical analysis, let's look at the bending curvature of the beam to understand how structural forces might have contributed to the collapse. To calculate this, we use the curvature formula. Let me break down what this symbol means. The K symbol is the curvature itself, M is the bending moment, E is Young's modulus representing the stiffness of the material, I is the moment of inertia. For our case study, we assume these standard values. The bending moment M is 500 times 10 to the power of 6 Newton millimeter. Young's modulus E is 25,000 megapascal, and the moment of inertia I is 4 times 10 to the power of 9 millimeter. When we put these numbers into the formula, we get the curvature of 5 times 10 to the power of negative 6 millimeter. Now, what does this number actually mean for the bridge? First, higher curvature means greater beam deflection. In simple words, the beam bends more. Second, if the curvature is excessive, it can lead to cracking and eventual collapse of the structure. Finally, we can conclude that during the construction stage, the loading or heavy forces may have increased the curvature beyond safe limits, especially when combined with the severe weather conditions mentioned earlier. Okay, so to wrap up our presentation, let's look at the final conclusions of our case study. First, to recap, the Hemiper Bridge collapse occurred on 29 May 2026 due to severe storm conditions. The structural failure involved the collapse of the concrete slab, the bridge pier, and the temporary shuttering system. By applying mechanics of materials concept, we can summarize our key findings into 4 main points. Number 1, beam shape directly affects structural strength. Number 2, large bending moments create high mechanical stresses. Number 3, when the stress becomes excessive, it approaches the yield stress of the material, causing the permanent damage. And number 4, increased beam curvature leads to very large deflection or bending. So, in conclusion, this incident shows us that proper structural design, strict quality control, and reliable temporary support systems are critical to prevent such failures in the future. That's all from us. Thank you for your time.